All right, guys. So we're going to be looking at this week a little bit deeper into the really complex topic of gravity. Now, last week we looked at some vocabulary and some concepts about gravity, and those were, I'm sure, a little bit overwhelming because they're kind of abstract. So hopefully what we're going to do today is make some of that a little bit more clear. Now, what I'm going to demonstrate for you, this is actually something you can do at home, and I would strongly recommend that you do. One, because it'll give you something to do. And science is about doing things, it's about experimenting with stuff. So mostly all we've been able to do this year is just kind of, sit and watch some things and maybe have a little bit of discussion, but it hasn't been like science should be. So here's an opportunity for you to actually do some science. I know many of you guys have been bored with the way things are, and I apologize for that. I wish you guys were here to do this with me. I'm sure Miss Flats feels the same way. So if you can do this, if you can get this set up, get your parents' permission, find a big space, get a bed sheet and some chairs that are about the same height, and stretch out the sheet to where it's nice and kind of flat all the way out. And then you're going to need some things like tennis balls, golf balls, uh, marbles, baseballs, softballs, different balls of different sizes and weights to make this work. So I've got lots of different objects that I'm going to use here, some of which will be, spherical in shape, some of them won't. But they're all going to demonstrate the main concept that we really need to understand about gravity. So all that stuff that we talked about last week with the vocabulary, the things like, dimensions and events and time and space, and the concepts that we live in four dimensions, and we're going to represent this here. This is representing space-time. So we've taken four dimensions and we've squeezed them down into two. Okay, but this is going to help us understand and visualize what that final concept we looked at last week, number 3, about how matter curves space-time. That's the big key. That's the big takeaway we needed to get. And we're going to focus that here today. So today is pretty much just going to be demonstration. And again, strongly recommend get your parents' permission. Do this yourself so that you can experiment and you can see for yourself what is really going on. So you're not just sitting there watching a video or having it playing in the background while you go do something else. Okay, so again, this is space-time. Now, most of the time, people consider reality, the world we live in, to be what we call fixed, unchanging. So that if I measure a mile in Washington State and I go to India and I measure the same thing, I'm still going to get the same measurement for a mile. It doesn't change. Same thing with time. If I measure an hour in Washington State and I travel to India and I take my stopwatch and I measure, it's going to be the same thing. So we consider space around us to be inflexible, like this. Okay, so this, I'll get a little bit closer. So this doesn't bend, I can't stretch it, I can't twist it, it's inflexible. And we often consider a reality to be the same thing, and like this, that it doesn't change. And this is where Einstein blew everybody's mind, because he said, no, reality, space that we exist in, the time that we live in, is not unchanging and inflexible and always constant. Reality, the space-time that we live in, can actually bend and flex and curve. And so this is what we're going to look at. And this was his idea of how gravity works. So remember, Isaac Newton said gravity is a force, similar to magnetism. And for hundreds of years, people thought that. Einstein said, no, gravity is not a force. There is no magical force that is reaching out, grabbing things, and pulling them in. This is what is happening. So here's an object that I've got. It's got some mass to it, some heft to it, some weight to it. So when I put this on the fabric of space-time, it sags. Space-time curves. The mass of this object causes the fabric of space-time to curve. And as I add more mass to it, it curves even more, even deeper. Let me move the camera a little bit so we can get a different angle, because right now you're looking top down, you can't see the curve quite as well. So here you can see that has caused a really big sag in the fabric. It's caused this big, deep well, so that if I were to take a marble like this, and I was to just set it up here, it's going to roll. Now, we would consider that if we were down here, if we were the person or the marble, we would say we were falling toward this. But we're not falling. There is no gravity reaching out, grabbing onto this marble and pulling it down. The marble is simply just following the curve of space and time. It's curved like this, and so we follow those curves. We don't fall, we follow. Okay, that's the difference. When you jump up and you come back down, you are not falling. You are, oh, I'm chipping my marble because it's in that metal. That's not good. You're not falling, you are following the curve of space-time. So in the future, don't say you're falling. Nothing falls. They follow the curve of space-time. And it's curved because of objects that have mass. And this is what Einstein said. This is what his whole thing was. Space-time stretches, space-time curves. And because of these curves, and this is what we're gonna, this is how we model this. Let me move the camera back up so you can see this motion better. There we go. So let's imagine this is the sun. In fact, hold on a second. Let me put the big giant orange thing there to represent the sun. All right. So there's the sun. Now the sun is very massive. So the sun creates a huge curve in space-time around it. All right. So here's a marble. Let's say this is a planet that's flying by the sun, and oops, it gets caught in that curvature of space-time, and it does this, kind of like an orbit. Now, eventually, that orbit is going to shrink and collapse, and it's going to run into the sun and die. And here comes another one. Do this one. Same idea. It follows the curve of space-time, wants it to come in this way. So even though its original direction was out here, space-time is curving this way, so it's curving the path like this. And that is where we get our orbits from. Our planets want to go straight, but space-time is not going straight, it's going curved. It's curving toward the sun, so the planets follow that curve, and they end up doing this. Now this one again, these are eventually going to slow down and fall in toward the sun and burn up. And I'm sure you can probably think and understand why that is happening in this model that doesn't really happen in space. What is different here? What is present here on this fabric that is not present in space? But this is our illustration of space-time, that objects with mass curve space-time towards themselves, and other objects follow those curves in, and that is what we call gravity. That is what we call falling. They're not really falling, they're following the curves. So again, I would really recommend that you do something like this at home if you can. It would be really, really helpful for you to try different things with it. So I'm going to try some different things here, and we'll see how well they work. And these will help give us kind of an understanding of how gravity, how space-time is affected by the massive object. So I've got smaller objects here. So here's one. It's a steel ball bearing about 1¼ inches, 1½ inches thick. Here's another one, steel ball bearing, but lighter. Now, you can see it wants to roll toward the heavy one. I have to kind of stop it because if I let it go, it's just going to roll all the way in like that. Because even though if I were to take this out, that is creating its own bend, curve, warping, whatever you want to call it. This is creating its own curve in space-time. But because it's smaller, because it has less mass, the amount of curve is much less. Whereas if I put this one down, this one is more massive, creates more of a curve. So less massive things are not going to be able to draw that toward them. They're going to be drawn toward the more massive things. So let's try other things. Let's take two of these smaller ones. Say I put one there. I don't need you, and I don't need you. And let's say over here, I put this one. Now this model is not great because I do have, oops, that still wants to roll in. I do have, because of, this is kind of a table thing, so I've got this frame here. So it's artificially creating a stiff edge here that doesn't want to stretch and bend and flex like it should. So it creates kind of an artificial slant. So we can't get a super perfect 100% neutral flat surface to work from. So you kind of have to use your imagination a little tiny bit with this. And acknowledge that there's going to be some incongruencies, is a great word. Incongruencies, things that don't match up. There's going to be some things about this model that don't match up with, reality, real space-time. So I'm trying to get this to not roll toward the other. See if I can get that to happen. It doesn't look like it wants to. It looks like it wants to keep rolling in. Like the other one's making just enough of a dent. I can't find a good spot. Come on, stop. Behave. No, it's not going to work. It's not behaving. That's unfortunate. Let's try something else. I've got some other objects here, and this is what science is all about. It's trying different things, testing something, see if it works, trying different things. And again, do this at home. Get your sheet, set it up amongst the furniture with some chairs and stuff, and try different things. Now, you're probably not going to have, like, this is lycra. This is a stretchy spandex type fabric. So it's going to stretch more than your average bed sheet will. Oops, that was wrong way. But it still works with your typical bed sheet. There we go. So there we can see there's two different, now these aren't like full baseballs, but they're kind of like the squishy type of baseball for like t-ball. But they're far enough apart, they're light enough that even though they do create a little bit of a divot, if you get far enough away, it's not going to be affected by this. This divot does not go on forever. It only goes out to a certain level and then things flatten out. It's like gravity does not go on forever. It goes out far, and the more massive the object is, the farther out it will go. Let's see if I can get a marble. I have to be very, very careful because if I go too fast, I'm going to fly off the edge. Okay, let's try another one. A different direction, see what happens. They seem to like that one a whole lot, don't they? Let's try the other side. Let's go out from this way. Yeah, this one seems to be making slightly more of a dent in the fabric of space-time, so it's drawing things in more than that one is. Let's look at some other stuff. Some other arrangements of things, items. So I'm going to bring this back because it's nice and heavy, makes a big old divot. Now I don't have anything else that's equally as heavy, but I think if I put these two in, these will make a similar amount of indentation. They're approximately the same amount of mass. There we go. Not quite. This is a little bit deeper of a dent, so not quite. Let's see if I add some more to that and make them equal. Put that there. Put that upside down. That's a little bit better. Okay, now, so I'm going to do some experimenting. I'll try some orbital mechanics between two stellar bodies. That's really high fancy scientific talk there for trying to get something to circle around two things out in space. So let's start out around the outside, see what happens. Interesting, let's try the other direction. Okay, so it kind of does a little figure 80-ish thing. What happens if I go in between them? It doesn't help if it runs right into it. Oh, too fast. Too fast and it flew off into space. Gravity couldn't hold it. Try something heavier. I got the larger one here. Let's see what happens if I do a larger one. Ooh, that one's got some really interesting patterns to movement. Let's try that one again. I like that one. Oops, too light. Too light. Not enough speed and it got sucked straight in. Oops, now it fell. Everything's falling apart. All right. Ah. I don't like it. That's really loud. I don't like that. I wish I had a softer version so it didn't like make that big loud noise. What if we go in between them? Interesting. So let's try a heavier one. Actually, I've got heavier ones. Still going. Okay. So it didn't go very far. Didn't do a whole lot. Let's try the other direction. Same thing. So let's go for another little one again. So you can see having two objects like this with the two different curves, anything that's flying around through them is kind of being pulled, not really pulled, but the space-time lines are curving in both directions. So sometimes it'll go this way, sometimes it'll go that way, sometimes it'll make a figure eight around them. So lots of different things happening. Again, do this at home. Get a sheet, get some chairs, stretch them out, get some small tennis balls, golf balls, little small things like that you can roll around. If you've got marbles, that would be even better because marbles work great with this. You just have to be careful because if you throw them too hard, it doesn't have to take much because marbles are light, so it doesn't take much to get them to go rolling off the edges and things. So then you might get in trouble for having marbles flying everywhere. That would be bad. But try this at home. Experiment with this. This again is our model of space-time and how objects with mass cause space-time to curve and stretch. Okay, curving and stretching of space-time. That's what this is modeling. All right. So when we come back, and again, this is not a perfect model. It helps us understand the motion of other objects. Like we can see how these marbles behave in that gravitational well and how they kind of sink in and circle around and kind of work their way in. So it helps us understand that motion so we can understand how orbits work really well. But what it does not do very well is, well, let's just imagine, all right, here we go, back to the beginning. And we've seen pictures and illustrations. I've shown several of them in a couple of the slideshows, and we'll be looking at more how when we draw this curvature of space-time, we put like the star or the planet here, and then we draw this curving and it goes underneath the star or the planet. And so we draw space-time going under whatever the object is, which then makes you think, oh, okay, well, if I'm standing here on the top of the planet, that would make sense because, I'm curving, I want to curve down toward the bottom like this. So that makes sense that gravity is going to make me want to go down toward the bottom of the state. But what about the people that live on the bottom of the planet, down here? What about the people down here? Wouldn't that make them fall off? If their space-time is curving underneath them, they're going to fall down onto this space-time. So how is it that people like in Australia, how is it that they don't fall off the planet when space-time is curving underneath it? Well, that's where this model is flawed. This does not represent what is actually happening with the curvature of space-time. And that's what we're going to look at next, and that's going to be our next block of concepts, is what is really happening? How is space-time actually being curved? This gives us a beginning of the understanding, but it is not the complete understanding. So our next section, we're going to look at, not the next section, but the next video, the next assignment and stuff, we're going to look at what is really happening. How is this really curving? What's the actual curvature of this? This just gives us a model so that we can roll objects on here and watch how they behave. Oh, no, didn't lose it. Good. Watch how they behave in this curvature so we can see these orbital patterns. But we don't live in flat two-dimensional space. And space-time does not curve under objects. We're going to look next week, or not next week, next lesson is going to be what is really happening. So stay tuned and hope you have fun.